Are you ready for a Raspberry Pi video? I sure am. Today we're going to take this Raspberry Pi Zero, hook it up to a motor driver, connect it to some batteries, and we're going to make a motor run. All we need now is a motor. Hey buddy, you're a robot, aren't you? Give me your motor. I got a motor. We're going to make this motor run, so let's keep watching.
This here is a robot motor gearbox. Inside of it, there's two electric 12-volt motors, one on the left and one on the right. If I apply 4.5 volts to the left side, it moves slow. And if I apply the same 4.5 volts to the right side, it will also move slow. I want it to move faster, so I'm going to take my 12-volt battery pack and I'm going to connect it to the wires on the left side. Now, assuming that your motor is rated for 12 volts, it should run twice as fast. That's what we want. Now let's go over to the other side. See if that's twice as fast. So why am I showing you this? I know you want to hook up a Raspberry Pi to make this motor go. The only problem is, this Raspberry Pi doesn't have enough power to make that motor go. Not only that, you probably damage your Pi if you connected the motor directly to it. So we're going to use this motor driver here. This one's called the L298N. You can find it online. Think of it sort of as an amplifier or something. But it doesn't actually amplify, it just lets a smaller voltage control a larger voltage. On the side of our motor driver, there's an out 1 and an out 2. I'm going to connect the two wires from my left motor onto it. It doesn't matter which order they're in. Looking back at my motor driver again, on the right side, there's an out 3 and an out 4. I'm going to connect those two to the two wires on the right side of my motor. And just like before, it doesn't matter which order they're in. Quick note to self, next time have longer wires. These are barely reaching. Now I'm going to hook up my 12-volt battery pack. And to make things easier, I'm going to put this little snap connection on here. It'll make things easier to work with. The red wire's positive and the black wire's negative. Let's hook these up here. Let's take our red wire, the positive one, and we're going to connect it to the 12-volt positive. That's right here. Now before we put our Pi on there, I'm going to demonstrate how to do this without a Pi, just to show you how it works. Instead of putting a Pi, I'm going to take our 4.5 volts battery pack and I'm going to hook that up in line instead of the Raspberry Pi. Now I'm going to twist both of the negatives, the black wires, together and I'm going to stick them into the ground right here. Once the ground is connected, you might notice that that little LED on the motor controller is lit up. Now watch me make the motor move by touching this wire to these jumpers. Jumper 1. The left one moves. Jumper 2. It moves the other way. Jumper 3. The right side moves. Now it moves the other way. Now it's time to hook up the Raspberry Pi. We already have this ground wire hooked up from the battery. We're going to hook it up to the ground on the Pi. The ground on the Pi, there's a ground, the third pin down, 1, 2, 3. Then we're going to take these jumpers off here. This first pin here is an ENA. We're going to hook that up to the GPIO pin 24. And that's like the 9th one down. 1, 2, 3, 4, 5, 6, 7, 8, 9. Next thing we're going to do is we're going to hook this yellow wire up to the N1. The N1 is going to be connected to the GPIO 17. That's the 6th one down on this side. 1, 2, 3, 4, 5, 6. After that, the N2 is going to be connected right here. And that's going to be connected to GPIO pin 18, which is on the other side. Now let's connect the second motor. The N3 here is going to be connected to GPIO pin 22. That's the 8th pin on this side. And then the N4, that's going to be the 8th pin on this other side. Last, we need to hook up the ENB. And that's going to be hooked up on the 11th pin here.
Let's hopefully we got that hooked up right. We'll connect up the power, and then we're gonna turn it on here. Uh-oh, this upside down. I think I made a boo-boo. Remember when I told you to take the ENA pin and connect it to the GPIO 24? Well, scratch that. Connect it to the GPIO 27 instead. I don't want to have to redo the video.
Open up your terminal on your device, or you can SSH to it, but that's another video. After you open up your terminal, I'm going to have you type in sudo space nano. Now we're going to name our file. I'm going to call mine motor_Charles.py. The .py tells your Raspberry Pi that this program is going to be written in the language of Python. As soon as you hit the enter button, you'll be able to type the code in. Well, you look at that. I got my own little Python editor here. Let's zoom in on it. Now, the first line that we're going to type in here. Now, remember, the capitals and spaces matter. Okay, so we're going to start out with small I-M-P-O-R-T, space, capital R, capital P, small I, dot, capital G-P-I-O, space, A-S, space, capital G-P-I-O. This line imports the rpy.gpio library, which allows your Python script to interact with the Raspberry Pi's GPIO pins. Also, the words as GPIO, this just renames the library to GPIO for an easier reference for the code. On this next line, we're going to import time. This imports the time module, which provides time-related functions such as delays. Now you see here, I have a line here that is started with a pound sign. It is just a label to help me, the programmer, understand where I'm at in the program. It really doesn't have anything to do with the actual program itself. Now on this line here, we're going to set the pin numbering system to BCM. This means that you're going to refer to the GPIO pins by their Broadcom numbers rather than their physical numbers on the Raspberry Pi. And of course, this red line is just another label line. See, it has a pound sign before it. You know, all these labels that we put in here, they might not be required to make this program run, but it sure makes things a whole lot easier. If I get lost and have to go back and refer to something, I can find my place easier. In this line where it says N1 equals 17, this line assigns the GPIO pin 17 on the Raspberry Pi to the N1 input on the motor driver. I'm just going to put a label on here. Next line, N2 equals 18. This line assigns the GPIO pin 18 to the N2 input on the motor driver. I better label this too. Don't want to forget. ENA equals 27. This assigns the GPIO pin 27 to the ENA. The ENA pin on your motor controller controls the motor speed via pulse width modulation. Say that 50 times. I'm going to label this so I don't forget here. Now what I want to do is I want to tell the Pi to set the GPIO pins as outputs. You know, you could also set them as inputs, but for our purposes, we're going to make them outputs. Let's label that. These next three lines configures the specified GPIO pins, N1, N2, and ENA, as output pins. This means the Raspberry Pi can send signals, high or low, to these pins. Well, I guess I better move this up. I'm running out of room. Now it's time to enable the motor. What this line does is it sets the ENA pin to high, in this case 3.3 volts, which enables the motor to connect to the motor driver. When ENA is high, the motor driver is active and can control the motor based on the N1 and the N2 signals. The try block in Python allows you to run a block of code and try to execute it. If any errors or exceptions occur during this execution of the block, Python can catch and handle them in a controlled way, rather than stopping the program abruptly. After the try command, you need to indent the next line at least 4 spaces. That will be part of the try block. What's a block? Here, I'll show you in a second. Let me get a couple more lines in. Now for this line, I'm going to label this, turn the motor in one direction. Before I have my motor move anywhere, I think I'm going to have it print a message on the screen to tell me that the motor is moving. Why? Because what if I hooked up one of the wires on my motor wrong? And maybe I think it's my Python code, but it's not. So I'm going to put this print command in saying motor running forward. This is going to display a message on the console indicating that the motor has started to run forward. Now for the command to turn our motor on. We're going to type in GPIO.output left bracket N1, comma, space, GPIO.high, right bracket. Don't forget the capitalizations. And this is going to set the N1 pin to high, which is full blast. It's going to be on. Remember, the N1 pin used to be the GPIO pin 17, but we renamed it. In this line, it's almost the same. You got the GPIO pin output will be N2, but we're going to make that low because you have to have one on and one off. By setting N1 to high and N2 to low, the motor is instructed to spin in one direction, commonly forward. But the motor driver uses these two inputs to determine the direction of the motor. Time sleep 5 keeps the motor running in a forward direction for 5 seconds before proceeding to the next action. Now let's go ahead and reverse the motor. We're going to print motor running in reverse. Then we're going to do the GPIO.output, but we're going to take the N1 and we're going to make it to low. And then this line's almost the same, but we're going to make the N2 to high this time, so we reversed them from before. And also, just like before, we're going to do a time sleep of 5 seconds. Moving on up here, let's work on stopping the motor. Start off with the print command saying motor stopped. In these two lines, we're going to set both N1 and N2 pins to low, which stops the motor by cutting off the power supply from the motor driver. Remember just a little bit ago, I was talking about this try block, right? Well, we're going to stop right here before we add any more lines, because we just finished our block. Let me show you. This is our try command, and everything here that is indented at least 4 spaces is our block. That means all these functions will be performed under the try command. All the ones that are indented anyway. Without indentation, Python would not know which lines of code belong to the try block and which ones do not. Indentation clarifies the block scope. Finally is a block of code that executes after the try and except blocks, making it ideal for cleanup tasks. Time to get ready to clean up. Oh, and by the way, indent these 2 lines because they're part of a block, the finally block. Just like before. We're finally down to our last command, GPIO.cleanup, left bracket, right bracket. This command resets all GPIO pins used for the script to their default statuses. This is important to prevent potential issues in future GPIO operations and to ensure that the pins are not left in an unintended state. To recap, this is all the code that we just did. You might want to pause the video, maybe you can write it down. I'll try to put it in the comments or something. Now you're probably going to want to save this. To save it, press Ctrl S. Wrote 41 lines here. Next thing you want to do to get out of here is press Ctrl X. To run our script, we're going to type in Python, then the name motor_charles.py. You might have named yours a different name. And if you did, type in that name. Okay, let's see what happens here. Press enter. I'm going to make a new file. I'm going to type in sudo nano w_key.py. This line brings in a special set of tools called rpi.gpio that lets your Raspberry Pi talk to its pins. Without this, your Python script wouldn't know how to control the pins to turn the motors on and off. This line brings the sleep function from the library, which allows your program to pause and set the amount of time. This line tells the Raspberry Pi to ignore certain warning messages. Sometimes, when you run your script multiple times, you might see warnings about the pins already being used. This line hides those warnings to keep your screen clean. These lines in this box right here assign specific GPIO pins to your Raspberry Pi to different parts of your motor controller. This line here tells the Raspberry Pi how to number the pins. It's a way to refer to the pins by their GPIO numbers instead of their physical locations. These lines set up specific pins like in 1, in 2, etc. as outputs. This means the Raspberry Pi will send signals out through these pins to control the motors. These lines set up pulse width modulation on a specific pin. Pulse wave modulation is a way to control how fast the motor spins by turning the power on and off very quickly. These lines set the specific pins to low, meaning they turn off any signals being sent to the motors. This ensures that when you start your program, both motors are stopped and not moving. Now it's time for the try command. It starts a section of the code where you try to do something that might cause an error. If an error happens, the program can handle it without crashing. Now this line is a print command. Now keep in mind, it's indented. You have to do that because it's part of the try block. This line displays a message to the user telling them what commands they can enter to control the motors. This line creates an endless loop that keeps running until you tell it to stop. This means the program will keep asking for user input over and over. Notice that it's indented because it's still under the try block here. This line waits for the user to type something and press enter. Whatever the user types is stored in user input. And I don't know if you've noticed this or not, but this line is also indented under the block of while true, which is indented under the try block. This line checks to see if the user typed the letter W. If he did, this is what happens. Now don't forget to indent these lines under the if. Well, anywho, these lines set the right motor to move forward by turning the in1 to high and the in2 to low. One off, one on. And these next two lines set the left motor to move forward by turning the in2 on, that's high, and the in3 off, that's low. By using the print command, we're going to show a message that the motors are moving forward. This next command checks if the user typed the letter S. And if they did, this is what happens. Don't forget to indent these lines, by the way. Oh yeah, where was I? These lines set the right motor to move backwards by turning the in1 off, which is low. And then the in2 will be on, which is high. Oh wait, there's more. I got two more lines here. These lines set the left motor to move backwards by turning the in4 off, which is low, and in3 to on, which is high. After that, we're going to use the print command to show a message that the motors are moving backwards. Now we're going to add the line to check to see if the user typed in the letter D for dog or doo-doo or something. Well, anyway, forget about the doo-doo and everything. This is what's going to happen when they hit the D button. These lines will make the right motor move backwards by turning the in1 off, which is low, and turn the in2 on, which is high. As for these two lines, they stop the left motor by turning in4 and in3 to low or off. Now to use the print command to show a message that the motors are turning right. This line here checks to see if the user typed in the letter A. And if the user types in the letter A, these lines will make the right motor move forward by turning the in1 on and the in2 off. And these lines over here will stop the left motor by turning both the in4 and the in3 off. Now we're going to use the print command to show a message that the motors are turning left. I bet you figured out by now what this line does. It checks to see if the user typed the letter C. And here's what happens. These lines turn off all the motors by setting all direction pins to low, which is off. And of course, you know, you're going to want to use the print command to show a message that the motors are stopping. The break exits the loop and ends the script. And then we have else. What else does is catches any input that isn't one of the expected commands, like W, A, S, D, or C. Now to use the print command to tell the user that the input they entered is not recognized and reminds them of the valid commands. This part catches an interruption, like if you press Ctrl-C on your keyboard, and it handles it gracefully. This line shows a message saying that the user has stopped this program manually. Finally! This section runs no matter what happens in the try block. Whether the program finishes normally or it gets interrupted, it will always execute the code inside finally. Then we got GPIO cleanup. It resets all the GPIO pins you used in this program back to their default state. This is important because it frees up the pins for all the programs and preventing issues if you run the script again. And last but not least, we're going to print on the screen GPIO cleanup complete. Program exited gracefully. Oh boy, I can't wait to run this. It's going to be fun. Don't forget to save your program. Hit Ctrl-S to save. To get out of this back into the terminal, hit Ctrl-X. Now that I'm at the terminal, I want to run my program. Oh, what did I name it? Oh, I remember now. Type the name that you named it, but put a Python before it. Python W_key_py. Enter. And I'll hit W. Enter. Ooh, it's moving forward. A. Stop it. Oh, it stopped. Now I hit S to go. Yeah, he's going. And then the D for stop. Hey, that's pretty cool. Now if I hit the C, it gets me out of here.
And there you have it! We got our motor controlled by our pie! I hope you liked our video today. Why don't you leave a comment in the section below? Put that in here. A dog!